Here is a digital logic circuit, a couple of gates wired together, and right beside it, the exact same logic as a PLC ladder diagram. In the next few minutes, you will learn how to convert a logic circuit to ladder, gate by gate, until turning one into the other feels automatic. Because here is the secret nobody tells you up front: a ladder diagram is not a different kind of logic. It is the same boolean logic you already know, just drawn as contacts and coils. Learn 4 little rules, and any gate circuit becomes a rung you can read on site. So let us lay out the whole map before we build anything. There are really only 4 translations to remember, and every one of them you have already met. An AND gate becomes contacts in series, one after another. An OR gate becomes contacts in parallel, 2 branches side by side. A NOT gate, an inversion, becomes a normally closed contact, and the output of the whole circuit, the thing the gates are driving, becomes the coil on the right-hand rail. That is the entire alphabet, and is series, or is parallel. NOT is normally closed, output is the coil. Master those 4, and you can translate anything. Let's take them one at a time. First, the AND gate. An AND gate turns its output on only when every input is on. Input A and input B both true. In Boolean, we write that as a .b. On a ladder, both must be true, has an obvious shape. You put the 2 contacts in series, one after the other, on the same rung. Power leaves the left rail, and to reach the coil, it has to pass through contact A, and then through contact B. If either one is open, the path is broken and nothing gets through. 2 conditions, both required, wired nose to tail. Series is AND. That is your first rule, and honestly it is the one you will use the most. Next, the OR gate. An OR gate turns its output on when any input is on, A or B. Either one is enough. In Boolean, that is a plus B. On a ladder, either one will do, means you give power 2 ways to get across. You put the contacts in parallel, 2 separate branches that split off the rung and rejoin. Close contact A, the top branch carries power. Close contact B, the bottom branch carries it instead. Close both, it still works. The only way to stop the coil is for both branches to be open at once. 2 paths, either one completes the circuit. Parallel is OR. Rule 2 done. Now the NOT gate, the inverter. A NOT gate flips its input. The output is on when the input is off, and off when the input is on. In Boolean, we draw a bar over the signal, or call it not A. On a ladder, we already have a contact that does exactly this, the normally closed contact. A normally open contact passes power when its signal is on. A normally closed contact is the mirror image. It passes power when its signal is off, and it opens up the moment the signal turns on. That is inversion built right into the symbol. So anywhere your logic has a NOT, an input you want to act on when it is off, like a NOT stopped or a guard not open, you reach for a normally closed contact. NOT is normally closed. Rule 3. And the 4th rule ties it all together, the output. In a gate circuit, everything flows toward one final output, the signal the whole diagram exists to produce. On the ladder, that output is the coil, sitting on the right against the return rail. The coil is the then do this of the rung. Everything to its left is the condition, the gates translated into contacts. The coil is the result. When the contacts complete a path from the live rail to the coil energizes and the output turns on. Break the path and it drops out. Contacts ask the question. The coil gives the answer. Gate output becomes coil. Rule 4, and now we have the full set. Here is the method that pulls those 4 rules into a repeatable recipe. Whenever you are handed a logic circuit, do not try to draw the rung straight away. Do this instead. Step 1. Write the Boolean expression for the circuit. Trace from the inputs through each gate and write down what it computes. The ANDs as dots, the ORs as pluses, the NOTs as bars. Step 2. Read that expression left to right into a single rung. Every and put those contacts in series. Every or split them into parallel branches. Every NOT, make that contact normally closed. And the whole expression drives the coil. Boolean first, then rung. Write it, then read it. Let us run that recipe on a real circuit. Here is our example circuit. We have 2 AND gates, and 1 are gate. The top and gate takes inputs A and B. The bottom and gate takes input C, and notice the little bubble on that input, a not on D. Both and gates feed into an OR gate. An OR gate drives output Y. So let us write the boolean exactly as the recipe says. The top gate gives us A and B, A.B. The bottom gate gives us C and not D, C.D bar. And the OR gate adds them together. So the whole circuit is Y equals open bracket A and B, close bracket, or open bracket C and not D, close bracket. Y equals AB, or C not D. That one line of boolean is the entire circuit. Now we just read it onto a rung. Read it left to right. The expression is 2 in terms joined by an OR, so straight away we know the rung has 2 parallel branches, 1 for each term. Top branch, the first term, A and B. That is an end, so contacts A and B go in series. A then B, nose to tail. Bottom branch, the second term, C and not D. Another, and so C and D in series, but D has a not on it, so D becomes a normally closed contact. C normally open, then D normally closed. Now the OR. We wire those 2 branches in parallel, splitting off the left rail and rejoining before the coil. And that junction feeds coil Y on the right. That is the finished rung. Trace it. Power gets to Y if A and B are both closed, or if C is closed while D is not, which is exactly what the gate said. We have just drawn the same logic a different way. Let's do a quick second one to lock in the not rule, because inverted outputs trip people up. Take a NAND gate. A NAND is just in and with a bubble on its output. It means not A and B. Now, you cannot put a bubble on a coil the way you put a slash on a contact. So watch how the inversion moves. There's a rule from Boolean called De Morgan's that says not A and B is the same as not A or not B. So a NAND becomes 2 normally closed contacts, A and B, wired in parallel, driving the coil. Then flipped to an OR, and both inputs became normally closed. Same trick works for an OR the other way around. When inversion sits on a gate's output, let De Morgan's move it onto the inputs, and you are back to contacts and coils. Step back and look at what just happened, because this is the whole point. Every one of those ladder rungs is nothing more than Boolean logic, drawn as contacts and coils. The gate symbols and the ladder symbols are 2 languages describing the exact same thing. Series is and parallel is, or normally closed is not, and the coil is the output. There is no hidden magic in ladder logic. If you can write the Boolean expression for a circuit, you can draw the rung. And if you can read a rung, you can write its Boolean. They're the same idea, wearing different clothes. So let us pin the 4 rules one more time, because these are the ones to carry with you. An in gate, contacts in series. An OR gate, contacts in parallel. A not gate, or any inversion, a normally closed contact. And the gate's output, the coil on the right rail. And the method around them. Write the Boolean expression first, then read it left to right into a single rung. It's in series, ORs in parallel, nots as normally closed, all of it driving the coil. Do that, and no logic circuit can surprise you. That is how you convert a logic circuit to ladder. 4 rules in a recipe. And is series, or is parallel, not as normally closed. The output is the coil. Write the Boolean, then read it onto the rung. If you want to go deeper on ladder itself, I have a full explainer on what ladder logic is, plus deep dives on how to draw a ladder diagram, how to read one on site, and a set of worked examples, all linked below. And if you want to watch your rungs run, inputs flipping, coils energizing, scan by scan, our sister PLC simulator does exactly that. Open the free editor, drop down 2 rails, and translate your first gate circuit into a rung. The link is in the description. Subscribe for a new diagram explained every week, and I will see you in the next one.